In part two of the project, we are going to actually design and simulate the computer system. And this is where the bulk of the work of the computer design comes in, because this is where you have the shell already completed. So you have the 8 design files that you've created for the entire computer system. You have a test bench that has been provided that is going to provide the clock and the reset and some starting values for the input ports. And you are going to go into each and every one of these VHDL files and implement the functionality. The way that you are going to start is you should implement the registers, or actually you should probably start with the memory system. So you're going to go into the memory system and you're going to code up everything that's in here. And so at this point we've covered how to do that and the details and the nuances of actually creating the VHDL. So you should have VHDL for the ROM and the read-write, and you've buttoned it up into the memory, and then you've gone into the data path and you've created the registers and you've created the multiplexing bus system, so bus 1, bus 2, and the 2 multiplexers. And then you have all these control signals that are coming out of the control unit finite state machine. The key to figuring out if your computer system works is to actually run a model sim simulation and watch each state of the control unit progress. And so what you need to do is at each and every state you want to make sure that all the output signals are correct, and also that they are making the registers do the appropriate data transfer that is expected. Okay, so to do this we are going to do a model sim simulation, and what I want to do in this video is give you some tips on how to get started in terms of debugging the system. Okay, so I've started up model sim and I have a folder with my 9 VHDL files in it, and so I'm going to go ahead and just start a new project. And you probably already have this from part 1 from the VHDL shell, but I'll just start from scratch here so we can all be at the same spot in this video. So I go into my computer folder that I have, and I have my project, and I say okay. And now I'm going to add my 9 files, and I go ahead and say okay, and I close. Now, remember that all the functionality of your computer system is dictated at this point using the program in your ROM. So if you want to see what your computer is doing, you should double click on the ROM. The way you want to start is you're trying to verify the 4 basic instructions of this computer system. So consider this program. You are going to first do a load A immediate with AA. If that instruction executes properly, at the end of that instruction, register A should contain the hex value AA. Okay? If you did that, a whole lot of things went right. That means you were able to fetch the opcode. You were able to decode it, and you were able to execute it, meaning that you went and retrieved the operand and put that operand as data itself into register A. Then you are going to do another instruction which is called load A direct from F0. If you recall, F0 is an input port. If you look at the test bench, you might wonder what is going to actually come in from address F0 if I do a load A direct. So you can go ahead and look at the test bench, and if you scroll down here, what you'll see is after the reset and the clock assignments, there's actually constant assignments to each of the input ports. So here you'll notice that port in 00 is connected to the CC. It's being driven with CC. So what I did in the test bench is I just put some starting values on here that are going to be very obvious. If you load from this, you'll notice that CC gets loaded in. So if you think about this instruction right here, load A direct from F0 is going to go out and it is going to execute, or it's going to go and read from the address F0, and if it executes properly, when this instruction is done, CC will reside in register A. So you will overwrite the prior instruction value in register A with the new value, which is CC. Okay, then you're going to do a store A direct to E0. Now, if you think about what's going to happen here, E0 is an output port. Okay, it's output port 00. And what are you going to write to it? Well, you're going to write whatever's in register A. From the prior instruction, that would be the value CC that we just loaded in from port in 00. So if you execute this instruction, you are going to know that it worked by looking at port out 00 and watching for CC to be present. Finally, you do your branch always to 00. Branch always 00 will put the program back at program counter value 0, and it will allow this program to loop indefinitely. The way that you know that this instruction executed properly is by looking at the program counter and seeing that it was set back to 0, 0 and watching the program execute starting back at address 0 containing the opcode for load immediate or load A with immediate addressing. So that's how we're going to test this instruction or this computer. The key to this really is that once you get one instruction working, the rest of them tend to be pretty easy because the first instruction takes so much debugging to make sure that you are actually able to present the program counter out on the address bus and retrieve the opcode, bring it into the CPU data path, and actually put it into the instruction register. If you can do that, a whole lot is going right. Okay, so we're going to actually start simulating this. I will tell you right now, mine works right now, and so what I'm going to do is I'm going to jump right to the finish and show you what it should look like if I run the simulation and I verify that these all work. Then we'll move into tips on how you debug it. Okay, so I've gone in here and I want to compile all of my files. Okay, so let me move this over so we can see the green, and I'm going to go compile all. All 9 were successful. I'm going to go over into my library and I will open my work folder and I'm going to load in the computer test bench. Okay, so now I have this big screen here and I want to look at my waveforms. Okay, and let me reposition it here so you can see it. This now is an interesting situation because I have my waveform and I'm going to run this for, let's run it for 1 microsecond. And the first question becomes, what are the signals that I want to look at in order to verify that this computer actually works? I can come over here into DUT, and one of the things that you're going to want to pay attention to is the levels of the hierarchy. So you'll notice that in DUT, if I click on it, I'm going to see all the levels that are at the DUT level. And this is when you instantiate the computer system. So you'll see clock and reset, and you'll also see all the ports, and then you get to see data in, data out, memory address, and memory write. Okay, so these are all the signals that you can see at the DUT level. If you come over to the CPU, you can see a whole bunch of stuff here. So you'll notice that in the CPU, you're going to see clock reset, but you're going to see to memory, from memory, address, write. You're going to see basically all the signals that exist at that level, and these are all the signals that go from essentially the control unit to the data path. Notice that the names that you're seeing right here are the instance names that I actually gave these in the VHDL. So for example, when I come in here and I have CPU underscore 1 and then under it I have CU underscore 1 and DP underscore 1, if I want to know where those come from, I could come back into my project and let me just look at the CPU really quick. Notice that when I instantiated these, I instantiated the control unit and I gave it an instance name of CU underscore 1. For the data path, I did a DP underscore 1. That gives me descriptive names that I can recognize later when I'm trying to do the simulation. So when I come back and look at the hierarchy when I'm loading signals, that's where all of this comes from. Okay. All right. So I come back over here into my sim tab, and if I come into the data path, I'm going to see a whole bunch of signals that I can add. Same thing with the memory. This becomes a very key thing when you debug, and that is understanding the hierarchy of where the signal that you're looking at is. For example, at the CPU, you could look at the address. Okay. Well, that address might be invalid, but then you say, well, where am I going to go figure out if that address is invalid? Well, you got to think, well, who produces the address? So then you might want to come into the data path and look at the address coming out of the data path. Those are two signals named the same thing, but they are at different levels of hierarchy. Okay, so you want to try to go back to the source that's driving that. Okay. All right. So if I was going to add a signal, I want to go into the control unit because that's where my finite state machine is. And let's just start with a couple signals like clock, reset, and current state. Okay. So I'm going to add to wave selected signals. And here I have my clock, reset, and current state. This brings us to saving a macro file. Okay. I have loaded these signals and I can even run them. Okay, and so I run them and they're doing all sorts of things, and I can even come in here, I can even come at the CU level, the control unit level, and let's say that I wanted to put like a register on there too, so I could do add to wave selected signals, and I just did that so that I have something that's actually data or a hex data, and I might take instruction register and say, okay, I want to change this radix to hex. So what I want to do is I want to add in all the signals that are important to me, okay, registers and the current state and all that sort of stuff. But I don't want to lose this information because it takes a long time to add the right signals that I want. If I just do add all signals in the computer, it's going to add hundreds and hundreds of signals, and it's very difficult to debug. So I want to go in and select the ones that I really care about. But you're going to be closing this project and opening it over and over and over. So you want a way to save the formatting. ModelSim gives you the ability to save this format by saving what's called a macro file, and it has an extension called .do. So I'm going to come in here and I'm going to go File, and I'm going to say, let me move this over so you can see it. So I'm going to say File, and I'm going to go Save. Okay, Save Format. And what it does is it says, oh, you want to save a do file? So it defaults it to be called wave.do, so I'm going to do wave1.do, and I go ahead and say OK. What that does is it allows me to, the next time I bring up a simulation, I then, before I add any signals, I simply go File, and then I load in that macro file. So if I came over here, let's say that I was going to do File, Load, bring it on the screen so you can see it, File, Load, macro file. Then I come in here and I can load that wave.do, and it brings in those signals in the same format. Okay? Alright, so that is key to actually building up a waveform that is meaningful. I'm going to go ahead and delete those, and I'm going to load in a predefined macro file that I did that has all the important ones to me. So I'm going to do File, Load, macro file, and I have this massive macro that has all the signals that I care about. And I'll go ahead and restart this simulation, and I will run it. Okay, look at this. I'm going to go ahead and undock this so we can see this waveform just a little bit bigger. And I'm going to come over to here, and I am going to make this the same size as the window that we see here. And then let's take a look at what's going on. Okay, so I fit this to the screen. I have a whole lot of information going. The first thing I want to do is figure out, how do I know if an instruction worked? Well, let's walk through the first couple instructions, or let's walk through one instruction at a time and figure out if it worked. Okay, so what we're going to do here is we will zoom out just a little bit. Let me zoom out and then I'll zoom in, and I want to get all the states in my first instruction, which was load A with immediate addressing. Okay? Okay, so I want to zoom in so that I can actually see the state names, and so I'm looking at my current state first. I'm going to look at these and make sure that it actually went through all of them. So I start with fetch 0, and then I went to fetch 1, fetch 2, decode 3, immediate 4, immediate 5, immediate 6, fetch 0. I'll just tell you, this works. But the way that I know that it actually worked was when I was done with this instruction, I wanted to see what the value of A was, because the instruction was load A immediate with the value AA. Well, look at right here. Right here, I can see the value AA pop into my register in the data path. That shows me the instruction worked. If it didn't work, what I want to do is I want to go through and look at every state in here and make sure that it did what I expected. For example, in fetch 0, what I was ultimately trying to do is take the program counter, which I have listed right here, and put it out on the memory address register. Now, the first time you do it, it's address 0, so it's not that, interesting because MAR started at 0, but you showed that 0, 0 went out to MAR, and then the MAR ultimately got out on, or was seen by the memory system. Okay? Now when you go to fetch 2, what you tried to do was increment the program counter. In fetch 1 you did increment the program counter, so you can know that fetch 1 worked because the program counter was incremented. So you're like, okay, the first two states worked. Fetch 2 was essentially bringing in the opcode, so you had a bunch of control signals, and then you loaded the information from memory into the instruction register. You know that that worked by looking at the instruction register, and it got the opcode 86. And it's like, okay, that was how you debug whether this is working. You go through state by state and watch the information in the registers move between registers. Okay, so I go through all of my states right there, and ultimately when it works, AA resides in register A. Let's do the next instruction, which was load A direct with F0. Okay, so I come over to here, and I've got fetch 0, 1, 2, decode, direct 4, direct 5, direct 6, direct 7, and at the end of this, I can jump all the way to the end and say did A get updated with the new value that was located at address F0? And the answer is yes. Look at, there's CC. So I look at that and I'm like, okay, this instruction worked. If it did not work, you would have to go back and think about all the things that happened. Was I able to take the program counter and get it out onto the memory address register? Okay, we got 2 in the program counter. It ultimately went to MAR. That worked. Then we incremented the program counter in the next state. Did the program counter increment? Yes, it did. It went from 2 to 3. Then the next state, I brought in the information from memory, which was the opcode of the next instruction, and I loaded it into instruction register. Did it make it there? The answer is yes, 8-7. Then you go through the states that went out and brought in the operand and loaded it into the memory address register. Did it get it? The answer is yes, it did get it there, and ultimately it did read from address F0. So that second instruction is verified. Okay, now I'm going to come over here and let's do the next instruction. There's only 4 that you're verifying. The next one is going to be store A direct. A contains the value CC. What I want to know is, can I store that to port out 00, which is located at address E0? If I want to know that, I need to see port out 00 on the screen. So when I scroll down and look at all the waves that I've saved, you'll notice that I have a couple ports. So port in 00, it had CC to begin with because that was driven by the test bench. But look at port out 00. After the instruction is done, it actually contains CC. So when this instruction was done, when I got done with the last state, I know that it worked because I saw CC right there. I've now looked at this and verified that I have executed the third instruction correctly. Finally, we get to looking at how we know if the branch always worked. I start by looking at the current state. Fetch 0, fetch 1, fetch 2, fetch 3, branch always 4. Branch always 5, branch always 6. And now I'm at the end. What does a branch always do? It takes the value from the operand and it stores it into the program counter. So if I look at the program counter, I see it incrementing 6, 7, and then here's a program counter load, and it got loaded with the operand of this instruction. It is now set back to 0, and that instruction operated properly, because if I go then to the next set of instructions, look at what happens. It starts back and it starts executing load A immediate. Okay, that's how you verify whether these instructions worked. So when you come in here and you're trying to figure it out, the way that you prove that it works is you take a screenshot of this screen and you got to put the signals on here that show it worked. You're going to need things like instruction register, IR load, MAR load, program counter, program increment. You need A and B and their load signals. For your own reference, you're going to need the bus system, because that's how you're going to debug whether things coming in and out of memory properly. You're going to need some ports. If you're accessing the ports, you need some. And then ultimately, when you do arithmetic, you'll need the ALU. But notice that I set up all these really nice signals, and I even went in here and did a right-click, add divider, so you can actually go in here and do a new divider, and that'll add a divider, and you can give it a descriptive name. Then once you have that format, you save it off. Okay, so that's how you actually walk through and make sure that the thing works. So now what do we do if it doesn't work right away? This is where you start getting into debug mode. So we've looked at how we can set up waveform formatting and save it so it's easy to find the signals. We've looked at what it should look like if it looks good, if it works, but what happens if it doesn't, and how do you even start debugging this? So let me go into here, and I have a mistake in my code. So what I have is I have this simulation going on, and I go ahead and run it, and when I go look at my waveform, I immediately notice that I've got these red X's on here. Okay, now I have my color set a little bit different from the default, but one of the things that I notice here is I look at this and I'm like, what's going on? I have X's here. Something must be wrong in my VHDL. So I go in here, and I always start with the state machines. So I've got fetch 0, fetch 1, fetch 2, decode. Those probably will always work because they don't depend on anything else. If you remember, our next state logic just traverses through them. But it's when you get past the decode, you go, oh geez, it went back to fetch 0. So something is really messed up in the decode step. So I can start thinking about, all right, let's break it down. Let's trace the error back to its origin. That is what you're always trying to do when you have a problem in your digital system. You're going to notice the high level issue, which in this state is that, okay, I first noticed that my current state didn't go from the decode to the proper state. It went back to fetch 0. So I say that's the first thing I noticed. Then you start saying, what caused that to happen? Okay, and then once you look at that, you might find another error and you say, well, what caused that to happen? And then you dig down a little deeper and you say, what caused that to happen? Ultimately, you can trace this all the way back to your VHDL and fix it. So let's do this for this particular example. I know that the decode looks at the instruction register to make a decision on what state to go to next. So I need to go look at my instruction register. Oh my goodness, look at this instruction register. It is messed up. When I look at the instruction register at a reset, I reset it to 0 all because it's a register. So that worked fine. But when we went to go ahead and load in the value from memory that should have been the opcode, it didn't have the right value. So now I need to think about, okay, where did the opcode come from? Well, the opcode came from memory. So I put out information, I put out address 0 on the memory bus, or the address bus, and I should have seen the opcode come back. So now I'm going to go back one state prior and say, did it ever come out of the memory system? So I'm going to scroll back down to here, and I'm going to look at what came out of the memory. Well, it's like, okay, well, I started with from memory, 8.6 did come out. So I can say, well, geez, look at that. The memory did actually it did produce the right value. So that's like, okay, well, that's great. So it came out of the memory, 8.6 came out. And if I look at my block diagram, I can think about this as, okay, the instruction register got screwed up. And so I want to make sure that something from memory worked. So I said, I put out an address, I assume it's 00, and something came back from memory, which was the right value. So I come in there and I verified that 8.6 came back. So now I say, well, did 8.6 ultimately get to where it needed to be? And if I look at this, if I know that 8.6 came from memory, I need to go look and make sure that it got onto bus 2 so that I could have loaded it into the IR. So let's go look at bus 2. I scroll down here and I look at bus 2. Holy moly, look at this. Bus 2 is completely screwed up. So I have identified where the issue might be. I have bus 2 not working, but I have the information coming from memory valid. So I'm like, oh, geez, what's going on? So what could possibly cause from memory not to get onto bus 2? Well, the only thing that we have here is this multiplexer. It's like, oh, geez. Well, I'm finally at a point where I need to figure out what's the VHDL for the multiplexer and see if it's correct. So I look at that and I know that the multiplexer is in the data path. So I'm going to go and I'm going to bring open the data path. And I want to scroll down to what assigns to bus 2. Well, look at, here's the multiplexer logic for bus 1. Here's the multiplexer logic for bus 2. Holy moly, somebody came in and commented out the code for that multiplexer. Well, all right, let's go ahead and uncomment that. I wonder what that was. So it's like, well, all right, well, let's make sure that it works. So I go ahead and I fix my VHDL code there. I need to go ahead and compile selected. And then I'm going to come back to, I'm going to restart my simulation. And then I'll bring up my waveform and I'll go ahead and run it. And look at this. Now I come back to my let me zoom full and then zoom in here. Now I come back and I look at my current state, fetch 0, 1, 2, decode, load A immediate 4, load A immediate 5, load A immediate 6, and then it repeats. And there's my value. Okay, that was a silly example, but it's very common. What you want to do is walk through state by state. Once you notice what the problem is, you want to then say, what could have caused this problem? And you say, what caused it? You go look at that in the simulation, okay? And you got all these signals in here, and then you just keep digging deeper and deeper and deeper until ultimately you find out the actual circuit that could be the issue. And then you go look at the VHDL. If you have a value on bus 2 and it's not getting loaded into the instruction register when you assert the IR load, go look at the VHDL for this process and make sure that it's okay. When you have information that's not getting put onto bus 1 correct, go look at the multiplexer logic for the bus 1 multiplexer. So this is the techniques that you use to actually debug this thing, and that is it. So once you start going through this and debugging these, every time you get one of these instructions to work, you take a screenshot of it, and then that's your deliverable. In your deliverable, you want to make sure that you have a screenshot that has the signals that are of interest. So in this situation, if I'm trying to demonstrate a load A immediate, I want to see the instruction register, the memory address register, program counter, A, B. I want to see, did the information ultimately get to A? When I go over and I do load A direct, I want to make sure that I see the information get into A, which is this guy, but I also want to see where it came from. I want to make sure that I have port in 00 on there so I can verify that that happened. Same thing with store A direct. I want to make sure that I can see the output port to make sure it worked. And then for branch always, I just want to make sure that I see the program counter. And that is how you ultimately verify your entire computer operation.